Alright, here we are on our last topic for Chapter 1, so hopefully you're still with me and you're still making use of the audio lectures, and we'll begin our discussion of density. And before we get right to it, you'll also appreciate, I think, that density is going to involve a lot of those problem-solving skills we just talked about, and the use of conversion factors in order to get the correct units. Density will have combined units, typically of grams per milliliter or grams per cubic centimeter, so we won't just look for a single final unit. We'll have a pair, at least a pair of units. Alright, so density is an important feature of matter. It compares the mass of an object to its volume, and as a result it's typically expressed mathematically as the mass of a substance divided by its volume. Standard units for gases would be grams per liter because they have a very low density. Those are the units that tend to make sense. Grams per cubic centimeter, which is typically used for solids, and grams per milliliter, which is typically used for liquids, are ways that we express those much more dense states of matter. And again, 1 gram per centimeter cubed is equal to 1 gram per milliliter. We just tend to use cubic centimeters for solids and milliliters for liquids, but a cc, a cubic centimeter, is equal to 1 milliliter. If we look at the density expression, you may have done nonsense in grade school where you looked at some sort of density triangle or whatever. That was all unnecessary. If you really understand units, it's pretty easy to look at the density expression. Density is mass divided by volume for an object, and therefore density equals mass divided by volume, and the units typically that we'll use will be mass in grams and volume in milliliters or cubic centimeters, or for gases we'll use liters. And of course, as I mentioned, we see that note that 1 milliliter is exactly equal to 1 cubic centimeter. Alright, so looking at table 1.13 or table 1.13 from our text, we have some common substances with their density listed. These are all at 25 degrees Celsius for the solids or liquids, and then that final column of gases, that's at 0 degrees Celsius and 1 atmosphere of pressure. That matters for gases because gases are temperature and pressure dependent, much more so than solids or liquids, which do have some temperature dependence, but pressure is relatively unimportant, at least at the regions we would tend to explore solids or liquids in this course. So as you notice, certain things are pretty low density. Cork, there's a lot of holes in cork, and it's largely air as well as the wood, and so it's a very light 0.26 grams per milliliter. Ice is just below liquid water at 0.92 as opposed to liquid water's value of 1.00 grams per milliliter. And when we get into metals like lead or gold, we see very high densities, 11.3 grams per milliliter for lead and 19.3 for gold. Contrast that with the liquids. At least the first couple liquids we list there are organic liquids, and they have values, densities less than 1. So gasoline of course is not a gas, it's a liquid mixture with a very high vapor pressure that allows it to be burned as gases in our internal combustion engine. But the liquid itself, the gasoline, is 0.74, so it's quite a bit less dense than water. As we see for water, that 1.00 is actually at 4 degrees Celsius, but it's not much different at 25 degrees Celsius. And then urine has a range of densities just above water. Plasma from blood is a little higher yet, and milk is even higher than blood plasma for humans. That cow's milk is even a little more dense. And then we see liquid mercury, incredibly dense liquid at 13.6 grams per milliliter. Notice the gases, not only are they small values like 0.090, we're also looking at grams per liter, so it's the unit is 1,000-fold larger. So the numbers are small and the unit's 1,000-fold larger. So when we look at things like carbon dioxide, 1.96 grams per liter, that would be still much less dense than water. So you wouldn't expect it to sink in water because it's a gas, it's grams per liter. Don't let that trick you. That 1.96 grams per liter is much less dense than 1.00 grams per milliliter for water. Now, just like in our previous lecture, we'll apply the same problem-solving strategy to calculating density that we did for converting units in the previous lecture. So we'll state the given and the needed quantities, we'll write the density expression, we'll express mass in grams and volumes in milliliters or cubic centimeters for liquids or solids. When we get to gases later on, we'll talk about volumes in liters, of course. And then finally, substitute mass and volume into the density expression in the way that we need to in order to calculate the density, or if we're given the density, in order to calculate the mass or the volume, whichever is missing. Okay, so looking at our first example problem with density, if a 0.258 gram sample of HDl has a volume of 0.215 cubic centimeters, what is the density in grams per cubic centimeters of the HDl sample? So applying our steps. Step 1, analyze the problem, looking at what we're given. We're given the 0.258 grams of HDl. We're given the 0.215 cubic centimeters of HDl. And of course, the question wants us to solve for the density in grams per cubic centimeter of HDl. So step 2, we'll write that density expression. Density equals the mass of the substance divided by the volume of the substance. So in this case, we have the mass and volume in the correct units of the same substance. Moving on to step 3, we'll express the mass in grams and volumes in milliliter or cubic centimeter. Luckily, the question already gave us those in the correct units. We don't have any conversions to deal with this time. It's always possible you'll have unit conversions that you'll have to be concerned with, but for now, things were nice and easy, so we can move on to step 4, where we substitute mass and volume into the density expression and calculate that final density. So density in this case equals 0.258 grams of HDl sample divided by a volume of 0.215 cubic centimeters of that HDl sample, and that gives an overall density of 1.20 grams per cubic centimeter, which we rearrange from a fraction to the more standard 1.20 grams per cubic centimeter answer at the end. So pretty straightforward. Hopefully everybody was able to follow there. If not, absolutely get in touch. Let's take a moment now to do a learning check and make sure that you're able to do on your own what we just very quickly did together there with the density question. So in this question, we have osmium is a very dense metal. What is its density in grams per cubic centimeters if 50 grams of osmium has a volume of 2.22 cubic centimeters? So go ahead, work through those different steps and arrive at your answer, and then decide is A, 2.25 grams per cubic centimeter correct, or is B, 22.5 grams per cubic centimeter the best answer, or is C, 111 grams per cubic centimeter best? So take a moment, solve the problem, check your answer against the choices, and make your selection. Pause the video now, or else we'll be moving on to the correct answer. Okay, so working through in step 1, we take a look at the given and needed quantities and analyze the problem. So we're given 50.0 grams of osmium, and we're told that it occupies a volume of 2.22 cubic centimeters, and ultimately we need the density in grams per cubic centimeter. So if we write the density expression, again, we're solving for density, so we want the form of the expression that says density equals mass of substance over volume of substance. Moving on to step 3, we express the mass in grams and volume in cubic centimeters. Look at that, I was nice again, and they're already provided in those correct units, so we have no conversions to worry about there. That means we can move on to step 4, substitute those values into the density expression, the mass in the numerator, the volume in the denominator, and we arrive at a final answer of 22.5 grams per cubic centimeter. Notice it's 3 sig figs because we had 3 sig figs in our mass and volume given in the initial problem. Okay, so that was your best answer choice. So B was the correct answer choice here, and hopefully that's the one you selected. So we were given mass and volume values there for those problems we've worked so far. One way to measure the density of solids, in particular irregularly shaped solids, is to take that solid and submerge it in a liquid of known volume. So if we look here, we've got a zinc ingot there, which is fairly cylindrical, but not a perfect cylinder, so we don't want to use the mathematical formula to find the volume of a cylinder. There's a bend to it. It's much better to go ahead and find its volume by water displacement, or liquid displacement, in this case water with some food coloring. So if we look, initially we had a volume of liquid of 35.5 milliliters. Then we introduced the zinc rod there into that known volume, and it caused the volume of the combination of liquid and zinc to rise to 45.0 milliliters. So the difference there, that final volume of zinc plus liquid minus the initial volume of liquid, gives us the volume of the zinc. So in this case, 45.0 milliliters minus the initial 35.5 milliliters, we very quickly solve for the volume of the zinc as 9.5 milliliters. So that's a very powerful technique for finding the volume of a solid, especially in the irregularly shaped solid. And we've known about this method for thousands of years now. You can thank Archimedes, who was charged with determining whether the crown that the king had made was genuine gold or if it was some alloy like brass that looked golden. And he went to the bath. The public baths in the ancient world were a popular place to soak. And as he put himself into the bath, he noticed the water level rose. And so he ran naked through the streets crying, "Eureka, I have found it." And that's how he determined that the crown indeed was not authentic gold, and the king had been swindled, and the crown maker would be severely punished. So again, it's a method that we've known about for some time, but it's as powerful today as it was for Archimedes a couple thousand years ago. So we found the density of that zinc ingot by water displacement. To find the mass is usually a much more straightforward matter of finding a analytical balance and determining the mass of the object. So in this case, that same zinc ingot, it's better to get the mass first, right? So the mass was measured before submerging it in the water so that it was clean and dry, and we found its mass to be 68.60 grams. So to find the density of the object, we take the mass divided by the volume. This time we have 68.60 grams divided by 9.5 cubic centimeters, and we find a density of 7.2 grams per cubic centimeter. So much more dense than water, but not nearly as dense as that osmium example from our learning check. Speaking of learning checks, let's try another one. In this case, let's try a learning check that involves that water displacement method for determining the volume of our object. So in this example, we're asked what is the density in grams per cubic centimeter of 48.0 grams of a metal if the level of water in a graduated cylinder rises from 25.0 milliliters to 33.0 milliliters after the metal is added. All right, so you've got a couple things. First, you've got to figure out the volume of the object. Then you've got to solve for the density, making sure you're in the correct units, and select your best multiple choice answer. Is it A, 0.17 grams per cubic centimeter, B, 6.0 grams per cubic centimeter, or C, 380 grams per cubic centimeter? So go ahead, find the solution, make your selection there for letter A, B, or C. Pause the video while you do that, and when you start back up, we'll look at the solution. Okay, so we'll apply our 4 steps to problem solving, and in this example we're given the 48.0 grams of metal, we're given the initial water level of 25.0 milliliters, and we're given the water level plus the metal of having a final volume of 33.0 milliliters. And ultimately we need the density, but of course in the middle we're going to have to find the density, or I'm sorry, the volume of the metal to get its density. So step 2, writing that density expression. Density equals mass per unit volume. Now here in step 3, we're going to want the mass in grams and the volume in cubic centimeters, and we have 2 volumes. Right now we have the volume after adding the metal to the water, and we have the initial volume of the water in the graduated cylinder. So the mass is easy. We have that given directly as 48.0 grams. That's 3 sig figs. The volume, when we take the final volume of water plus metal, 33.0 milliliters, minus the initial water volume of 25.0 milliliters, we end up with 8.0 milliliters. And of course, since 1 milliliter is equal to 1 cubic centimeter, we can multiply through by that conversion factor to go from milliliters to cubic centimeters. We still end up with 8.0, but as we notice, because of the subtraction sig fig rule, right? The subtraction sig fig tells us we should have the same number of sig figs in our answer as the least significant, least significant. In this case, they're both to the tenths place, but the least significant decimal value. And so we've gone down to 2 sig figs, right? 8.0. Everything in the initial problem had 3 sig figs, but because we needed that difference and we applied the subtraction sig fig rules, we end up with just 2 sig figs for our volume, and obviously our final answer will therefore have just 2 sig figs. Okay, so as we move on to step 4 and substitute in the mass and volume into the density expression, we find that we end up with a value of 6.0 grams per cubic centimeter. So 2 sig figs for our final answer, and in this case that was answer choice B from the multiple choice option. So hopefully you got that. Not only you got the right answer, but you understand why B is correct. You didn't just get lucky picking B as your answer choice. Okay, if not, then obviously work some additional problems from the text or check the homework set out, and of course get in touch with me if needed. Alright, so we've worked some density problems now. Let's talk about sink or float. So ice floats in water because the density of ice is less than the density of water. Aluminum, on the other hand, sinks in water because its density is greater than the density of water. You have to be careful, though. We do also have surface tension involved. So sometimes you can have objects that are slightly more dense than the liquid will stay on the top of the liquid until the whole surface wets, so until you break that surface tension. So just be careful, and of course if you mold an object in such a way to trap air inside, like these big steel ships, they'll float because the overall density of the system, the air plus the metal, is less than the density of water. So you have to be careful, and you have to think about how much water you displace and all that. It's a bit more complicated than simply sink or float, but in theory, if something is less dense than a liquid like water, it should float on top. If it's more dense, it should sink, but again, you've got much more at play, since we know that steel ships can float on water and should float on water if they're designed correctly. Now, so far, we've always been solving for density. We've been given mass and volume, or at least some way to find the volume if we have the water displacement method used. But we can also think about density as a conversion factor. So ultimately, density can be, say, 1.00 grams per milliliter for water. Well, we could have 1.00 grams over 1.00 milliliters, or we could have the milliliters in the numerator and the mass in the denominator if we need to use the density as a conversion factor. So just realize it can work that way as well. We're not always just going to be solving for density by having mass and volume given. Sometimes we'll be solving for mass by knowing the density in the volume, or the volume by knowing the density in the mass, for instance. Okay, so ordinarily we write densities as grams per milliliter, so a density of 3.8 grams per milliliter can be written as an equality. That means 3.8 grams of that substance equals 1 milliliter volume of that substance. And if we want to look at it as a conversion factor, we can have the more standard 3.8 grams over 1 milliliter, or if we need to cancel units of grams for a given question and we have the density provided, we would do 1 milliliter over 3.8 grams. The conversion factor that's appropriate for our problem is the one that we would select. Okay, so let's apply this in a problem. So if the density of milk is 1.04 grams per milliliter, how many grams of milk are in 0.50 quarts of milk? So working it through, we'll start with step 1. Look at what we're given and what we need to analyze that problem. We find that we're given the density in units of 1.04 grams per milliliter, and the volume is given as 0.50 quarts. So quart should set off some red flags right there. It's not the same volume unit as the density is given in, so we're going to need a conversion factor or two at least. And ultimately, we want to find the mass. Moving along into step 2, we'll write our plan to calculate our needed quantity. So volume, because of how it was expressed, we'll need to go ahead and convert from that US quart to some sort of metric factor. And if we go right into milliliters, then we can use that density, which is already in grams per milliliter, as a conversion factor to ultimately find the mass. Step 3, we can write the equalities and conversion factors. In this case, because this was a question that was not on the test, we can look up the conversion factor, and we can find that 1 quart equals 946 milliliters. On an exam setting, I might give you that one. I might give you 1 or 2 other conversion factors to get yourself from quarts into milliliters. And then finally, a milliliter equals 1.04 grams because of the density of the object. So we can go ahead and use those conversion factors in whichever way is needed so that we can cancel the units that we want to cancel and be left with units ultimately of grams for this question. Okay, so now as we move on to step 4 and set it up all correctly, we take that 0.50 quart of milk that we're initially given, and we have the conversion factor of 946 milliliters over 1 quart. Notice because we've switched systems, that has 3 sig figs. The 946 is not exact. We had just 2 sig figs in our initial quart of milk volume, so we're not limited yet by those sig figs, but we do want to keep track of it. And then finally, we'll multiply by 1.04 grams per 1 milliliter, the density of milk. And as we cancel units, the quarts will cancel, the milliliters will cancel, we'll be left in units of grams. And if we do our math correctly, when we multiply the 0.50 by the 946 by the 1.04, we should end up with a value of 490 grams to 2 sig figs, right? Our initial 0.50 quarts of milk was 2 sig figs. We're doing multiplication and division here, so we want the final answer to have the same number of sig figs as our least significant value. So 2 sig figs was our least significant value in the calculation, and therefore 2 sig figs is the number of sig figs for the final answer, the 490 grams of milk. So hopefully that last question went well. Let's go ahead and pause for a learning check to make sure that things are making sense. In this example, we're told the density of octane, a component of gasoline, is 0.702 grams per milliliter. What is the mass in kilograms of 875 milliliters of octane? So if we take a look here, we have our answer choices: A, 614 kilograms, B, 0.614 kilograms, or C, 1.25 kilograms. So take a moment, work through the problem using our 4-step strategy, and take a minute to pause the video here first, because it should take you a couple minutes to solve this, and then finally make your answer choice A, B, or C, and start things back up. Of course, notice also we want the final answer in kilograms, and we're given grams per milliliter, which is our standard way of expressing density. So we will have a metric conversion at the end, in addition to using the density as a conversion factor here. All right, so go ahead, pause now, and start back up when you're ready to check your answer. Okay, so the first step, of course, is to state the given and needed quantities, analyze the problem. Here we're given a density value for octane of 0.702 grams per milliliter and a volume of 875 milliliters, so 3 sig figs for each of those, and ultimately want an answer in kilograms. So notice our density is given in grams per milliliter, so we'll be doing some converting at the end to get the final unit of kilograms. Okay, moving on to step 2, we'll write our plan to convert the given values to that final needed unit. So first we'll have milliliters, which was the volume of octane given, and then we'll use the density as a conversion factor, and then finally a metric conversion factor to go from grams to kilograms in order to arrive at our final answer with the correct unit. Moving on to step 3, we know that based on the density that was provided, 0.702 grams of octane equals 1 milliliter exactly. We know, of course, that 1 kilogram equals exactly 1,000 grams, and we have the conversion factors possible based on those equalities. Obviously, we're going to want one over the other. We're going to want the 0.702 grams in the numerator because we're going to want the milliliters to cancel with the milliliters of octane given in the question. And then we'll want kilograms in the numerator so that we'll have the 1,000 gram down below to cancel with the grams from our density conversion factor. Okay, moving on to our final step, we set up the problem and cancel units and calculate the answer. So we have 875 milliliters, which we could put over 1. Again, if you prefer it that way, that's fine, that's legitimate. Then we'll multiply it by the density, 0.702 grams over 1 milliliter. We'll cancel those milliliter values. Of course, the density, the 0.702, is 3 sig figs. The 1 milliliter in the denominator is infinitely significant. And then finally, we'll multiply through by 1 kilogram over 1,000 grams, another case where we have exact values, so they won't affect sig figs. So far, everything that is measured has 3 sig figs, and we expect 3 sig figs, therefore, in our final answer, since this is a multiplication division example. We've canceled our units correctly. Milliliters cancels with milliliters in the denominator. Grams now in the numerator cancels with grams in the denominator. And so we end up with a final value of 0.614 kilograms, 3 sig figs based on our 3 sig figs for the density and volume. So that makes answer choice B the correct value. Hopefully you got B correct, not just because you guessed, but because you were able to go through this solution process. If you're still having trouble with that, try a couple end of chapter questions, check the homework questions, and then obviously get in touch with me if it's still not working for you. Sometimes you may see specific gravity listed on a particular chemical reagent or in a safety data sheet or someplace, and specific gravity is the relationship between the density of a substance and the density of water. It's determined by dividing the density of the sample by the density of water, and it's unitless because the units of density for the sample and water would both be the same here if we're going to make a meaningful comparison. So just be careful of that. Typically, specific gravity, because we assume a value of 1.00 grams per cubic centimeter for the density of water, so typically the specific gravity will be the same numerical value as the density of the substance, but it won't have the units of grams per cubic centimeter or grams per milliliter or grams per liter because of the fact that you've canceled those out. And the reason we bring up specific gravity is because that's what's measured if you ever use an instrument known as a hydrometer. You get the specific gravity, which is, of course, related to the density, and assuming that the water is 1 gram per milliliter, it would be the same as the density of the substance in grams per milliliter. But again, if we wanted to solve density rigorously, we use the gram mass and the milliliter volume from water displacement or some other method. Specific gravity is just a relative amount compared to water, but because of water being assumed to be 1 gram per milliliter, specific gravity usually turns out to be the same as the density for the substance without the units. Alright, so before we leave chapter 1, we've got one last learning check to see how you do with all these concepts, in particular density, now that this is our final topic for the chapter. So, which of the following samples of metals will displace the greatest volume of water? A, 25 grams of aluminum, which has a density of 2.70 grams per milliliter. B, 45 grams of gold, which has a density of 19.3 grams per milliliter. Or C, 75 grams of lead at a density of 11.3 grams per milliliter. So obviously what you'll need to do is find the volume of each of these objects. Since they're all more dense than water, we expect them to sink if they're solid ingots of the metals, and therefore the volume of the metal object will be the same as the volume of water that it displaces. So go ahead and find the volumes. Whoever has the largest volume of those will be the correct answer. They'll displace the greatest volume of water. So go ahead, solve it, decide on A, B, or C for your answer choice, and then pause the video now, start it back up when you're ready to check your work. Okay, so this was a tricky one if you didn't know exactly what you were solving for, and the correct answer turns out to be A. So if you listen to my advice there, you're solving for the volume of each of those objects, and the one with the greatest volume would be the object that displaces the most water, because the volume of the object is the amount of volume of water it will displace. So if you take a look for A, you're taking that 25 grams, multiplying it by 1 milliliter over 2.70 grams to find the milliliters of aluminum that would occupy that mass based on that volume. So it turns out to be 9.3 milliliters of aluminum. For B, the gold, there's a lot more of it, 45 grams mass-wise, but because of its very high density, when you multiply the 45 grams by the 1 milliliter over 19.3 grams, you end up with just over 2 milliliters of gold, giving that mass of 45 grams. And then finally, the lead, which is significantly more dense than aluminum, but almost half as dense as gold. You have a larger volume because 75 grams times 1 milliliter over 11.3 grams gives 6.6 milliliters, but still not as large a volume as you had with the aluminum. Aluminum being a light, low-density metal, just 25 grams of it displaces more water than 45 grams of gold or 75 grams of lead. So hopefully you were able to solve that just fine and get the correct answer of A. If not, try some end of chapter problems, check the homework questions, and certainly reach out to me if you need to. So here we are wrapping things up, not only on the density topic, but on all of chapter 1. Hopefully you found these lecture audio supplements to be helpful, and hope to have you join me for chapter 2.